If you have questions and don't want to be recorded, I will be recording the Zoom, and just send me a chat. What we're going to do is just go over Newton's laws, Newton's first and second law, and show you how to do Newton's law problems. So Newton's laws, the first law is known as inertia, right? And that's a tendency for objects to remain in their current state of motion. That's the first law. So if they're at rest, they want to stay at rest. If they're moving, they want to stay moving. And the second law, a net force causes an acceleration. So a net force causes acceleration. So when you have multiple forces acting on an object, let's just draw it. I know my drawings are really bad, but if you have an object and you have multiple forces, right, F A and FB, if FA is greater than FB, the object's going to have an acceleration to the right. And if FB is greater than FA, the acceleration will be to the left. So that's essentially what we're being told here with Newton's second law. Depending on which force is bigger, the acceleration is going that direction. And it allows us to solve for those things. With the second law, we get the formula for weight. The second law formula, is F equals ma, where this F is a net force and then your acceleration vector for the system. And from this, we get the formula for weight. Weight equals mg. So if we have an object, and let's say its mass is 10 kilograms, right? The weight vector is always down, and that equals m times g. So 10 times 9.8 is 98 newtons. So this is how we solve for weight. Weight is always negative. It's always going to be downward. So that's one thing that we want to always remember. When we're dealing with Newton's second law, we're going to write it two ways. We're going to say the sum of the forces in the x equals max, and the sum of the forces in the y equals may. So we're going to solve Newton's law vertically and horizontally. This is a sigma. The symbol here is a sigma. Can't write sigma, and that means to add or to sum. So we add up all the forces in the x or all the forces in the y, and that gives us our net force and all the masses as well. So let's just apply this, take a look at some problems. The first problem I want to look at is something that we kind of glossed over in chapter 3. I didn't go over it because it's kind of a special topic, but you're going to need it here in chapter 4, especially when you get into a friction. If you have an inclined plane, so here we have an inclined plane, and the inclined plane is at some angle. Let's say the angle is, I don't know, we'll make it easy here on us, 30 degrees. And on this angle, we have a box, which I'll have to draw this box, I think. Can I rotate this? Okay, I can rotate. So on this, we have a box here. I'll draw this box. And this box has a mass, we'll make it easy, of 5 kilograms. So the weight of the box is straight down. (49 newtons). Now the question is going to ask, what are, I'll type it, it'll be a lot easier to read. What are the components of the weight that act parallel and perpendicular to the plane? So we have this object on this inclined plane, and there's a perpendicular component that holds it to the plane, right? That's your perpendicular. So that would be this component that holds it to the plane. And then we have a parallel component that pulls it down the plane. So we have these two components acting on our object whose weight was straight down. Right, there's our weight. So we have to find the value for these two components. And you can see if I draw a coordinate axis at the tail of this, right, at the weight's tail, that we have a positive x, and I have my y going the wrong way, but whatever. Well, it should be like this, a positive x and a positive y, right? Let me get these on the actual thing. And this gives us our components of the system. Now, we learned last chapter how to find components using cosine and sine. So what we did is we drew a vector triangle. So we took our hypotenuse, we took our x component, and we took our y component, and we made ourselves a vector triangle. Where this is wx, the horizontal component of the weight, and this is wy, the vertical component of the weight, and they're at this angle. And we know the weight is 49 newtons. Now this angle here is 30, so if I draw a drop down, this angle here is 60. So our angle here is 60 degrees. So to find the horizontal and vertical components of the weight on an inclined plane, right, Wx equals mg cosine theta. I don't know how to make an angle in here. I'll just write it out. 49 cosine 60, which equals 24 and a half. And it's negative, it's down the plane. And then Wy equals 49 sine of 60. $42.44. So these are the components of the force that hold the object to the plane. Does that make sense?
How did you get 60?
I know that's pretty ugly looking. So if I draw that line straight down there, right, that's our weight. You see this little triangle? Oh, I didn't want to do that. See this little triangle? That's 60 degrees there. And then our x component comes down like this. So if I take our x component here, see how it comes down? That's a 60-degree angle.
Okay.
Does that make sense?
Yeah.
So that's how you find the components that hold you to the plane itself. Do you have questions there? Anybody? There's only like 5 people that stayed. I guess everybody else is, maybe I made the test too easy. Oh, there's a whole bunch of people here still. It was just my little screen. Woo, good. I was nervous everybody would leave. Maybe I'll just make the test harder next time, and those people that aren't here, they just won't have all the information. Do you have any questions on this? Anybody? This is a time to ask. This is kind of tricky, and we're going to use it a lot. We'll use it in the lab. We'll use it in our friction problems. There's also a problem like this on the video. So if you didn't catch this, watch when you're watching the video, maybe it'll make a little more sense.
Wait, I have a question.
Oh, no. Yeah.
Is that 49 with the cosine 60 and sine of 60? Is that supposed to be negative when you put in an equation?
Like right here?
Yeah.
It doesn't matter either way.
Okay.
But if it works, if it's easier for you to put it in there so you don't forget, you can.
Okay, thank you.
I usually don't put it in because I can just based on my coordinate axis, I can see that they are positive and negative, you know what I mean?
Yeah.
Which quadrants it in, but it's just a double negative, but if it helps you do it, can't hurt.
Okay, thank you.
Now let's do some more Newton's law problems. And they're all, I wish I could write a sigma with my crazy thing. I'll just use a big E for sigma. They're all going to be adding the forces together. So we're just going to look at some easy ones. We're going to start it off, and all we're going to do is just do some example problems of that. So let's just give this shape here a 500 kilogram mass and say that there's a couple of forces acting on it. Let's say there's a force acting this way. I want my forces to be a different color. So there's a force acting this way. And we'll go force acting this way. I'll give them some values. We'll say A equals 50 newtons and B equals, even though it doesn't look like it, 75 newtons. And the question would ask something like, find the acceleration of the system. The way we would solve this problem, we would say the sum of that E is a sum, a sigma. I don't have a sigma. Sum of the forces in the X equals MAX, and that's also a subscript at X. It's just neater if I write it out. So we're going to have two forces. We have B minus A equals MAX. That X again is a subscript. You see why it's B minus A? Because B is a positive force, A is a negative force. Then you'll have 75 newtons minus 50 newtons equals 500 kilograms times AX. AX equals 25 divided by 500. That's that 0.02, 0.04. The acceleration in the X equals 0.04 meters per second squared. And that's how we solve out that problem. Seems easy, right? Any questions there? Well, you know we're not going to stay easy forever. So let's take another problem. Here's the one we're going to do in the lab. We have a surface. Now you guys are going to be solving for friction, but the idea is we'll just take a look here and it's got a pulley on it here. And an object's on the surface. And we're going to do this without friction. And there's another object over here hanging down. Made that pretty big. And they're connected by a light wire. So wire goes out, and then it hangs it down. Like so. So what happens here is this object, we'll call it B and A. Object A, when it's released, is going to fall to the ground. So object A falls. Since there's no friction up here, B is going to follow A. So the force in this acting on B, let's look at the force acting on B, is from the weight of A. So the force here acting on B, right? The force acting on B is from the weight of A. Weight of A. Thank you. So that's the force that's pulling this system. B's weight right? The weight of B isn't moving this system at all. All that's doing is keeping B here. But the weight of A down here that's what's moving the system. So now if we give masses to them, we'll say the mass of B and B. I need to see the subscript, sorry. If I say the mass of B is 20 kilograms and the mass of A is 12 kilograms, what's the acceleration of the system? Right? What's the acceleration of this system? So we go over here to Newton's second law. We say, okay, the sum of the forces in the x, because we're assuming B is moving in the x, equals the mass of the system times AX. So to help us solve this problem, we're going to draw what we call a free body diagram. This is the mass that is being accelerated in this direction, right? That's the acceleration, AX. There's no force to the left here. The only force causing the acceleration is the weight from A. Well, how much mass is being accelerated? Is it 20? Is it 12? Or is it 32 kilograms? So when you look and see the picture of what's going on, you can say, oh, the only force in the x is WA. That equals the mass of A plus the mass of B times the acceleration in the x. The acceleration in the x equals ma times g over ma plus mb. AX equals, I'm going to run out of room, 12 times 9.8 over 32. I'll move it over here. AX equals 3.68 meters per second squared. And that's how you solve these problems. You have to take all the mass and you have to do the forces that are acting on them. So whenever we're doing these problems, we're always going to draw what we call a free body diagram, which you'll see up here at the top, right? This is our free body diagram. This is what allows us to see what's going on. So we can accurately represent the forces and the masses. Does anybody need anything clarified on this problem? All right, so that's kind of tricky. We're starting off, we're going strong here. Let's try another problem. Again, I'm just going to go with a rectangle. And let's put a rectangle, make it red again in the middle of the screen. I can add as many forces. Let's this time let's give an acceleration. We'll say the acceleration equals negative 35 meters per second squared. Negative 35 meters per second squared. We know that there's a force acting on this object to the right, and we know there's one acting on the object to the left. Let's say the one to the right is, I don't know, 1,000 newtons. We'll call that B. We'll call it A. A equals 1,000 newtons, and B equals 600 newtons. And our goal here is find, oh, this isn't going to work. Sorry. Find the mass of the object. My bad. This has to be different. This can't be 600. This has to be 1,600. All right, so you guys try this at your seats and give me a thumbs up when you get it right. Or get it. All right, so it's looking good here. Let's give this a look-see, see what we got. I'm going to say sum of the forces in the x equal max. A minus b equals m, which is what we're looking for, times negative 35. M equals 1,000 minus 1,600 over negative 35. (17.14 kilograms). Oops. Oh my goodness, this thing is so sensitive today. How'd we do there? Anybody have any questions or anything? All right, let's try another one. This time, I'm going to change this up just a bit and leave the box, just erase everything. I don't know why the box is staying out there. We're going to take it to a little bit harder this time. We're going to combine what we just did. So what we're going to do is we're going to make a table. I'll make it brown just to spice things up. I got myself a table. And we're going to put two pulleys on the end just like before. And we're going to stick a box on the middle of the table. We're going to take two strings, run them over each side of the pulley. Make that pulley bigger. I can't get far enough away here. And we're going to attach two masses to them. So we're going to have a mass here and a mass here. Not the best drawing you ever did see, but whatever. This is going to be object A. This is object B. And this is object C. The mass of A equals 0.5 kilograms. The mass of B equals 1.2 kilograms. The mass of C equals, looks bigger, doesn't it? We'll make it 0.8 kilograms. Your goal, find the acceleration of the system. That's the goal here. Now we had multiple, remember this goes back to the one we did with the weight. What I want you to do is just take a moment and draw the free body diagram for this situation and give me the thumbs up when the free body diagram is drawn. Just a free body diagram. That's all we want to do here. All right, I'm going to draw it up here on the screen for you. Show you what it looks like. I'm just going to increase the size. So what's being accelerated is A plus B plus C. That's our mass, right inside there. The force pulling us to the left is the weight of A. And the force pulling us to the right is the weight of C. The weight of B is pulling downward. It's not causing acceleration in any direction. It will, if there was friction here, it would increase the friction. Now that you have the free body diagram, is there anybody that has a question on the free body diagram? All right, at your seats, solve for the acceleration. All right, that's more than half of you now. So we had WA, WC. So we're going to write it out just like we would. We're going to say the sum of the forces in the X equals MAX. WC minus WA equals MA plus MB plus MC AX. So remember, WC is going to be 0.8 times 9.8, and WA is 0.5 times 9.8. So 0.8 times 9.8 is 7.84. And this is 4.95. 4.90, sorry. 4.90 newtons. So we have 7.84 minus 4.9 equals 0.5 plus 1.2 plus 0.5 equals AX. AX equals 2.94 divided by, oh, this is 0.8, sorry, 2.5. I was thinking 2.5 in my brain. 1.18 is the acceleration in the X direction formed by this system. So this is a force, what we call a force system, multiple masses working on each other. Does anybody have any questions there? How'd we do? Did you get it right? Thumbs up if you got it right, 1.18. One person? One person got it right? All right, that's not good odds. Less than 10% of you. Does anybody have any questions on that? Where do you think you went wrong? If you have a question or you see where you went wrong. I did such a good job of explaining it. All right, let's try a different one. This time we are going to take a circle, just a giant pulley. And we had two strings hanging from our giant pulley. We have one here, right? And it wraps around the top of the pulley. It's just hard to draw that. And one here. And from these strings, we have a couple masses. We got mass A and mass B. We'll say A equals, I don't know, 2 kilograms. and B equals 1.2 kilograms. So what's the acceleration of this system? We have two forces acting here. I'm going to show you how to do this. Two forces acting. We have weight from B, and we have the weight from A working against each other. So this is 1.2 times 9.8, and A is 2 times 9.8. So we're both pulling downward, so it's hard to draw a free body diagram. So what I'm going to do is stretch this out into a vertical free body diagram so you can see how the forces work against each other. Well, this force here, if we stretch it out horizontally, is pulling to the right. And this force from A is pulling to the left at 2.98. Now we have a nice, neat free body diagram. We know that this mass is A plus B. Now we can solve the problem. So try this. Do the math at your seats to solve this problem and find the acceleration. We'll say the sum of the forces in the x equal max. 1.2 times 9.8 minus 2 times 9.8 equals 1.2 plus 2 times ax. Ax equals 1.2 times 9.8 minus 2 times 9.8 over 3.2. Negative 2.45 meters per second squared. And the negative just tells us that it's accelerating towards a 2 kilogram mass. So that's how we solve that problem. And we'll do one more. Does anybody have anything clarified here? All right, let's take a look at this here problem. We have this object on an inclined plane. It has a mass of 45 kilograms, so the weight of the object, I'll do a different color. The weight of the object is straight down. We know the weight of the object is going to be 45 times 9.8. 441, I think, right? 441 newtons. That's the weight of the object. There are two components acting on it. We have the x component down the plane and the y component perpendicular to the plane. Those are the two components acting on this object. Where the y component is actually, even though we draw it in a right triangle, the y component is actually in the center of the object. So it's what holds it to the plane. We make a right triangle though, so we can do our trig and solve for it. This angle is 22. That means our angle up here is 68 degrees for our vector triangle. Well, the y component is holding it to the plane. So the component that causes the motion is wx. So if we draw our vector triangle, right, that's 68. This is 441. Wx equals 441 cosine of 68. 165.20 newtons. To find the acceleration of the system, we say the sum of the forces in the x equal max. Remember, this is our positive x, this is our positive y. The only force acting in the x is wx. So we have 165.20 divided by 45 equals ax. 3.67 meters per second squared. There's our acceleration in the x direction. How'd we do? Thumbs up if you got that right. Anybody? Thumbs up if it makes sense now. All right, so my suggestion was for you all, that's the end of, I'm not going to do any more problems today. I don't want to overload you too much. Is we